Hello, my name is Hervé Cottin and I'm an astrochemist. I'm working at the LISA laboratory at the University Paris-Est Créteil. In this lecture, I'm going to talk to you about prebiotic chemistry in the solar system. What I call prebiotic chemistry, as you will see, will be more about looking for organic molecules in the solar system, how we look for them, and how they can be somehow related to the origin of life. As you may hear, read, know, more and more we hear in the news that some molecule has been detected, for instance, methane on Mars, and question is raised whether it is related to life or not, whether a detection of jets in the atmosphere of icy moon such as Enceladus can give us hints about whether or not there is life in the ocean buried under the ice because some hydrogen in an amount that was not expected is detected. Or more recently, phosphine, a molecule that was not supposed to be detected in the atmosphere of Venus, has been supposedly detected. It's debated. It's not yet sure whether or not phosphine has been detected. But in the news, you hear about this unexpected molecule and you hear about maybe a detection of life in the atmosphere of Venus. Facing all those news, facing all those announcements and observations, we have to keep the feet on the ground and try to get some background regarding the organic chemistry in the solar system, what can be considered as being something really relevant regarding the prebiotic chemistry. The lecture outline of my talk today will be first to discuss about the ingredient of life and discussing the prebiotic chemistry in the solar system, first in the small bodies. That will be the main topics covered in my talk because I'm working on that topic. So I have a limited time, so there will be a bias, and I announce my bias in the beginning. My focus will be on the organic compounds detected in the small bodies of the solar system. But I will also discuss a little bit about Mars and about the icy moons and their environment that has become in the recent years the new El Dorado for astrobiology in the solar system. So first, ingredients of life. What are the ingredients for life? If you go on the internet and, for instance, description of space mission, here it's an extract of a NASA mission called Europa Clipper, and you can read that the ingredients for life might be found on the Jovian moon Europa, and those ingredients are water, chemistry, which is related to organic chemistry, and also energy. So why is it considered as ingredients for life? We have this conception that if somewhere we find beyond Earth, at the same time, at the same place, a mixture of liquid water, organic matter, which are molecules which are based on carbon, and also energy, life might appear. And all our search in the solar system, but also beyond the solar system, is based on the search of these three ingredients that could be mixed together and that might lead to the origin of life. But at this stage, we have no idea whether these ingredients are necessary, whether each time we find those three ingredients together, life may arrive. We know that it happened on Earth, but actually, we don't know if it happened on Earth because of these ingredients. And it's not a theorem. It's not yet demonstrated. It should be regarded as an axiom or a postulate as defined in classic philosophy is a statement that is so evident or well established that it is accepted without controversy or questions. But now, at this stage of research in science, we should question these ingredients of life. And we are at the stage to be able to question whether or not these ingredients would lead to life, or whether or not these ingredients are necessary or not necessary for the origin of life. Let's talk a little bit about these ingredients. First, water. We talk about water related to life. We have to think and remind us that it's liquid water that is supposedly to be important for the origin of life. Actually, water is quite common. It's the second most abundant molecule in the universe after hydrogen. So water is everywhere in the universe. What is specific, probably for the origin of life, is water in the liquid form. Why? Because water has physicochemical properties that are found together in water and usually separately in other solvents. It is considered as a molecular matchmaker. Organic chemistry in water, in liquid water, behave differently than in other solvents. And in liquid water, we think that we will be able to have the wide range of organic reactions that otherwise are found separately in other solvents. But to account for the origin of life, we need many different organic reactions, and we think that liquid water is probably the only one to account for such a diversity of organic reactions. But, except on Earth, liquid water has not yet been observed beyond our planet. There are hints, of course, that there may be liquid water under the surface of Mars. There have been radar detections stating that under a huge amount of ice at the southern pole of the red planet, there might be liquid water. But it's derived from radar measurement, and it's still discussed, still disputed. We know from geological measurements that there has been liquid water on Mars in the past, but not anymore. Also, under the icy surface of the Jovian or Cronian satellite, we have very good confidence that there should be liquid water below the ice, but it's indirect detection. It has not yet been observed directly. So there is no reason to consider that liquid water doesn't exist beyond Earth. But we have to keep in mind that it's at present day, it has not been directly, irrefutably observed. And last but not least, nobody has ever proved yet that liquid water would lead every time to the origin of life. And water can also be considered as the best or the worst thing for life, because some of the organic reactions that we think are absolutely necessary for the origin of life are not evident or easy to conceive in liquid water. On this slide, you can see a very simple organic reaction, which is the association of two amino acids. Alanine and glycine would react to form a peptide bond and to form a dimer of amino acid. This is the first step to build larger peptide chains and, in the end, proteins. To make this reaction happen, it releases a molecule of water. The peptidic bond formation releases a water molecule. If you are in liquid water, it's an equilibrium. If you are doing this reaction in liquid water, then the equilibrium should be displaced to the left. So the thermodynamics says that the hydrolysis of peptidic bonds is favored in liquid water rather than the association of amino acids. So it's not because you will find, and we'll discuss that later, amino acids in comets, in meteorites, and you will hear and you might think that these are the bricks of life, prebiotic elements. It's not because you find those elements that are key to prebiotic chemistry, or at least seen as key for prebiotic chemistry, that you solve the mystery of the origin of life, because linking those prebiotic molecules is what organic chemists working on the origin of life right now are focusing, and it's far from being evident or an easy problem to solve. You need to account for probably catalytic synthesis on mineral surfaces. Maybe you need to have organic chemistry that occur on a dry state, and so liquid water is not necessarily the best friend for the origin of life. You might need liquid water at some stage, but maybe you need absence of liquid water at other stages. For instance, on this scheme, so the idea is not to get into the details here, but it's a mechanism that has been proposed for the synthesis of chains of amino acids. And just, if you're not a chemist, you will have a very hard time to get into the details of this mechanism, but just consider the colors. What is in blue are the reactions that occur in liquid phase. What is in dark are the reactions that need to occur in the solid state, in the dry phase. So that is probably a requirement for amino acid connection together, and more recently a paper was published about the fate of nucleobase on the primitive Earth, and this paper was also discussing this necessity, this requirement of getting from liquid phase to dry phase, and this paper was proposing the requirement of warm little ponds, so sequences occurring in warm water, ponds of water. These ponds of water would evaporate, enabling new sequence of organic reactions in the dry state, and then after rain pouring on this surface, another sequence in liquid phase. I insist on that to say that at the current stage of our knowledge about the organic chemistry leading to the origin of life, liquid water is probably mandatory for some of the organic reactions we are interested in, but for some steps we might need absence of liquid water. What about carbon? We have a lot of questions whether or not life should be based on carbon, whether or not extraterrestrial life could be based on other elements like silicon or other elements. Well, one thing is that carbon is quite an abundant element in the universe, and its chemical structure also enables a lot of bonds with other carbon atoms, but also hydrogen, oxygen, nitrogen, sulfur, phosphorus. And it's also an observation that in the interstellar medium or in the atmosphere of other planets, there is an active organic chemistry based on carbon, and it's ubiquitous. Everywhere we look in the universe, we see a large diversity of organic molecules based on carbon. So the organic chemistry is not necessarily the chemistry of life, although you will find textbooks of organic chemistry with a front page showing very nice trees, flowers, butterflies to make you want to buy this book rather than another organic chemistry textbook. But, organic chemistry occurs everywhere in the universe, without a chemist, without life, but it also tells us that It's probably the best ingredient, the best strategy for us to build our search for life beyond Earth, because, well, it leads to a large amount of molecules, and we know at least that on the Earth we found life based on carbon, and every life on Earth is based on carbon. But it has never been proven that complex organic chemistry would necessarily need to lead to life. There is complex organic chemistry everywhere in the universe. And actually life is rather a selection among this complexity, an organization among this complexity, rather than an explosion of diversity of organic compounds. And you will see we found a very huge amount of complex molecular structures in meteorites, in comets, but it's more a problem for the organic chemists or the organic chemists thinking about the origin of life than a solution, because we need then to make an inventory of that and think about why life chooses those ingredients rather than others. But we will talk more about carbon in a few minutes. Last ingredient, energy. For many, energy is enough. Energy in whatever state it can be found. So whether it's just heat, whether it's energy that can be released by redox reactions, or energy that can be brought by light, radiations. But is any kind of energy okay for the origin of life? Or do we need more a specific kind of energy, at least to start the process? And is the energy that is needed to sustain life nowadays the same that was needed to start life? And I'd like to stop a few minutes on these topics, because it's quite interesting to have that in mind, and at least to keep that in mind for the future and to the search for life beyond Earth. Well, here I just show a definition of life, a definition that was proposed by a chemist colleague called André Braque, saying that life is based on little robots making copies of themselves and capable of evolution. Evolution being understood here by mistakes during the reproduction. And you can see on the scheme a robot with only one arm in an environment with parts, and this robot with one arm would make a copy of itself, and, well, with one arm. And then, by mistake, this little robot will make a copy of itself with two arms. Well, you might think it's better to have two arms to build a copy of itself. Yes, in a specific environment, it's better to have two arms. But if in this environment you lack this part that allows to build arms, being a robot with two arms will not necessarily be an advantage. It's better to reproduce with one arm, because you will make more copies of yourself, than to reproduce with two arms, because you will make less copies of yourself. So I like this definition because it's not based on liquid water, it's not based on organic, it says just about a process. But, well, it's not meaning that we will find robots everywhere in the universe. And here I show you another way to reflect on this definition. If you're not a chemist, just focus on the left part of the slide. If you are a chemist, maybe you will be more familiar and you will understand better what I understand on the right part of this slide when I show a scheme showing the energy and the advancement of the reaction. So consider the robot I was talking about as being the C molecule on the scheme. On this scheme is shown an autocatalytic process of replication of the C molecule. C molecule would react with R reactant with energy to create an intermediate, which is shown here as I. And the intermediate would spontaneously either go back, because it's an equilibrium, so make another back again C and R, or if the autocatalytic process is working, I would dissociate into two molecules of C. So you start from one C molecule, and in this loop, you end with two C molecules. So this is an replication, an autocatalytic replication. C auto-replicate its reproduction. What is important is that from time to time, you might have a mistake in this replication. So instead of going back to C, you will create C prime. And if the new reaction with C prime is favored thermodynamically or kinetically, then you will change the loop C to C into C prime to C prime. And what is important is that you must have this loop turning like that and not going backward in the upper part of the mechanism. And to prevent these reverse reactions, it has been proposed that it has an energetical cost. It must require energy that is higher than a specific potential. And some recent paper discussion about these topics have proposed that this initial energy required to make this loop operating must be at least in the visible domain or in the UV domain, but it requires photons. It would not work with a simple input of heat in the form of heat, or even with redox reaction, it would not work. So based on these studies, life could start only at the surface of a planet, because only at the surface of a planet you would get energy in the form of photons, of radiation, at least above this energy level that would prevent the autocatalytic systems to go back and prevent the replication of the compound C. So that's an important thing to keep in mind. It's discussed in the community. I'm not saying that it's the definite answer to the question of energy for the origin of life, but it's the current state of research. So, after having browsed through those three ingredients, I will now focus more into the organic chemistry. What are the reservoirs of organic matter, of carbon in the solar system? Where are we going to hunt for them in the solar system? Both to explain maybe the origin of life on Earth, because we know that Earth has been bombarded with meteorites from asteroidal or cometary origin, and some ingredients that have been involved to the origin of life in the primitive Earth may have been brought from those exogenous sources. And what is interesting is that the comets orbiting the Sun now, or the meteorites falling on Earth now, have the same composition than the comets or meteorites falling on the primitive Earth. So we have a direct view of the ingredients that were falling on the Earth when life arose. I won't have time to discuss about the syntheses that may have occurred in the atmosphere of the primitive Earth that were explored by Stanley Miller and other scientists since its historical experiment in 1953. I will also skip very quickly about syntheses that may occur in the environment of hydrothermal vents in the oceans of the primitive Earth. But we will look at what fell on the Earth. So the small bodies can be regarded as organics of the shelf that we can still explore and study right now. So what is found in a specific category of meteorites called carbonaceous meteorites? There are meteorites that are made of metals, made of mostly stones, but there is one family of meteorites called carbonaceous chondrites, which is rich in carbon, and I will discuss those meteorites right now. You must know that currently roughly 10 tons of meteorites fall on the Earth every year. It was maybe and probably much more on the primitive Earth. And there are 10,000 tons of micrometeorites that are falling on the Earth right now. They are not all containing carbons and organic molecules, but it's still an ongoing process. The Earth gets material and organic material from space. On the left, you can see a picture of a fragment of the famous Murchison meteorite that fell on the Earth in 1969 in Australia. And it's a very famous meteorite because it fell in the desert, in a dry place. It was recovered and analyzed very quickly to prevent contamination from the Earth environment. And we learned a lot from this meteorite. On the right, it's a picture of the Orgueil meteorite that fell in France more than a century ago. And in this meteorite, organic compounds have also been found. So what we know from those carbonaceous chondrites is that we can find up to 5% in mass of carbon. So it's not the majority of the meteorite which is made of carbon, but a significant amount of carbon and organic molecules. And in the Murchison meteorite first, and in many other meteorites later, we have detected organic material, and among this organic material, it can be noted that more than 75 amino acids have been detected at a small level, 10 to 100 parts per million in mass, but it's detectable. It has been proven that it's not a terrestrial contamination because among these 55 amino acids, only 8 are found in the proteogenic, in the proteins, so are involved in the life on Earth. And most of those amino acids are found in racemic mixture, which means that for amino acids, you can find 2 3D structures, which are both images one to another in a mirror. Life uses only one of these 2 configurations, the L configuration. And in the Murchison meteorite, you find both configurations almost in the racemic 50-50 abundance. Beyond those amino acids, recent studies have shown that there are a lot of organic structures, and likely millions of diverse organic structures can be found. This is a reflection of a complex organic chemistry that occurs during or before the formation of the solar system. And these organic compounds are stored in those meteorites, and they are delivered to Earth, but also to other planets. Mars, for instance, has been bombarded, and those organic molecules have been delivered to the planets of the solar system. Here you see a pie chart showing the diversity of organic compounds that are found in the carbonaceous chondrite. roughly 50% are carboxylic acids, but you will see that you will find aliphatic compounds, alcohols, ketones, aromatic compounds, amino acids, nucleobases also are found at small amount in carbonaceous chondrites. Another important aspect is that some amino acids are also found in a slightly excess in the L configurations, which it's been proven that it's not a terrestrial contamination because this excess is found in amino acids that are not used by living by life on Earth, such as isovaline, but it means that this enantiomeric excess may have started by processes that occurred before the origin of life on Earth. It doesn't mean at all that life appeared before Earth, but it means that the chemistry started and maybe the physicochemical processes that lead in the end to the fact that life shows L configuration rather than the D configuration maybe occurred in space, and I will talk about that. So I said that in the carbonaceous chondrites, 5% in mass is made of carbon and organic compounds, which means that 95% is inorganic matter, minerals, metals, and so on. But among those 5%, I've talked about amino acids, carboxylic acids, aliphatic compounds, and all those molecules I've just discussed. They are considered as soluble organic matter, which can be extracted from the meteorites. But it represents only 10 to 25% of the carbon that is found in the meteorites. You have to keep in mind that most of the carbon that is brought to Earth by meteorite is found in the form of what we call insoluble organic matter. And this insoluble organic matter is a complex network of carbon with aliphatic, aromatic structure, with some oxygen, nitrogen, included in the carbonaceous matrix, but this material is very difficult to characterize because it requires a lot of analysis to really understand how it is structured, and we struggle also to understand how it formed and how it had been incorporated to the meteorites. I've talked also about micrometeorites. They represent most of the flux of exogenous delivery to the Earth. So some of the micrometeorites are made of minerals and metals, but some of them are made of carbon, at least a small fraction, and even some micrometeorites called ultracarbonaceous Antarctic micrometeorites can contain up to 50% of carbon, and sometimes with also a significant amount of nitrogen. So they are tiny, they are difficult to handle and to analyze because of their size and the small amount of material that is available for analysis. But well, that's another source of organic material, and most of this material is also found in the form of insoluble, complex organic material. So let's stop with meteorite and move to some other objects of the solar system that have some links to the meteorite. These are the comets. So what do we find in terms of organic diversity and in terms of amount of organic material in comets? So I will focus now on the recent results that have been reported after the Rosetta mission. Rosetta mission was a European space mission that has been sent to a comet and that stayed near a comet during 2 years, from 2014 to 2016. And we have been able to analyze the comet. So there have been a lander, Philae, that landed at the surface of the comet and made measurements for a few days only, and I will discuss more about what we learned from the main spacecraft, which made analysis during 2 years at the comet. So before the Rosetta mission, we knew that comets were made of minerals, ice, dominated by water ice, but also CO2, CO, ammonia, and other compounds that were detected from the Earth. On the right part of this slide, you can see what is the diversity as observed in comets from the Earth. And you see that there's a lot of molecules, water, CO, CO2, and the rest of the list are organic compounds with methane, ethane, formaldehyde, methanol, and other compounds. The abundances are given related to the abundance of water. So water is 100%, and for the other compounds, it would be 10, 1, 10 to the minus 1, 10 to the minus 2 or 3. Tiny amounts of compounds have been detected related to the amount of water. If you see pale blue line on this slide, it represents the diversity of amount that has been measured from one comet to another. For instance, for CO, you can find comets where the abundance of CO is below 1%, and comets where the abundance of CO related to water is above 10%. So all the comets are not the same. So it's not thanks to Rosetta, because we know this comet precisely, at least as precisely as we can with this space mission. It doesn't mean that we know everything about comets, because there is a large diversity between comets. So the Rosetta spacecraft left the Earth in 2004, and it reached its destination, the comet 67P Churyumov-Gerasimenko, in 2014. 10 years of travel, because we didn't want only a flyby and a few minutes of observations. We wanted to be on the same orbit than the comet is around the Sun. And so the Rosetta spacecraft was orbiting the Sun at the same place and at the same velocity than the comet Churyumov-Gerasimenko. And the spacecraft was a flying laboratory with many instruments, and I will focus on the mass spectrometers that were analyzing the gaseous phase, the Rosina mass spectrometer, and the Cosima mass spectrometer, who was analyzing the refractory phase, the dust particles that were ejected from the nucleus. So this is Comet 67P. You've probably all seen those wonderful pictures. And here you see an infography that was produced by the European Space Agency, just to illustrate the diversity of compounds that have been detected in the atmosphere of Comet 67P. So some of them were already known and observed from the Earth in other comets, but there has been many new detections. So to make it nice to see and not a very hermetic table for chemists, the molecules have been grouped by category which are not chemical category, but the smelly molecules have been put together, and the heavy molecules have been put together and represented by an elephant, for instance. Well, that's the infography for outreach, showing the diversity of compounds that have been detected. I will come back to that later, but you can see that the lion, the king of the zoo, shown in this picture, is glycine, the simplest amino acid that has been detected during the mission. So this is a kind of table you can find in science paper, showing the diversity and the abundance, again plotted referenced to the abundance of water. And you can see that there is a lot of organic compounds detected in the gaseous phase. The Rosina mass spectrometer was just letting the gas get inside the mass spectrometer and analyzing, fragmenting, and the molecule. And a mass spectrometer is measuring the mass of the molecule, and from the mass and the fragments, we can go back to the initial organic molecule. But what I want you to keep in mind that behind this huge diversity is the abundance. And in comets, there is a large diversity of organic compounds, but if you count the amount of organic compounds, the abundance is below 2%. If you sum everything, you stay below 2% relatively to the abundance of water. So large diversity, but well, a relative small amount of in total of organic compounds. And if you focus on glycine, which has been detected, some estimations say that it's about 200 part per billion in abundance relative to the water ice. So this is a detection of glycine that has been advertised and discussed a lot when it has been detected, because glycine is kind of an iconic molecule. I have to remind you that glycine was also detected in the samples that were brought back to Earth by the Stardust mission, the NASA Stardust mission in 2006, and the analysis of the samples that were returned to Earth concluded that some glycine was detected. But at that time, we were not sure yet whether the glycine was in the dust collected and brought to Earth, or if the glycine was produced during the analysis on Earth from precursors that were on the comet. So with Rosetta, glycine has been detected in the atmosphere without any analytical process. So now we know that glycine is present in Comet. But finding glycine is not such a big deal. It was expected, and it doesn't reflect a very complex organic chemistry that would give us breakthrough regarding the origin of life. Because here you can see a very simple chemical scheme that reflects the chemistry that can occur in ice, in a condensed phase at low temperature. And when you have an ice made of carbon dioxide, CO2, mixed with methylamine, CH2NH2, just if you warm a little bit this ice, those two compounds will react together and form a salt. It's an acid-base reaction, and we will form a salt, methyl ammonium methyl carbamate. And if you add some photons, some UV photons on this salt, you will form another salt, methylammonium glycinate. So in 2 steps, from CO2 and methylamine, and those two compounds are detected in the atmosphere of the comet. In 2 steps, you get to glycine. And as I told you earlier, the main question for prebiotic chemistry is not whether or not glycine was present on Earth, and the chemistry leading to the formation of glycine. No, the question is how you get amino acids linked together to form protein in the end. Another thing to mention is that only glycine has been detected in the comet, maybe because the other amino acids are present at lower abundances, or maybe because from experimental studies in the laboratory on the Earth, to get other amino acids, you need liquid water. At this stage, we are able to form glycine in ice without liquid water, but for other amino acids, you need liquid water at other stages. This slide just to show that even if the Rosetta mission ended in 2016, there are still publications, still papers, still discoveries. For instance, this paper was published last year in 2020, showing evidence of ammonium salts that were detected in the Comet 67P. And these ammonium salts are extremely interesting because, well, if you are a chemist and if you are working in the laboratory, what you use actually to start your reaction in the laboratory are salts. They are the actual reactive compounds you use to start your organic synthesis. So, well, these are new ingredients that are present that, well, for some reasons that are too complicated to explain right now, were not seen from the beginning of the investigation of the Rosetta mission, but, well, we've been able to prove they are present. I've talked to you about what was found in the gaseous phase of the comet. Now I'm going to talk to you about what was found in the solid phase, not at the surface of the nucleus, but rather in the dust particles that were ejected from the nucleus of the comet. So the comet is made of ice and dust, and when the ice is sublimating, when the comet approaches the sun, it drags some dust particles that are ejected in the atmosphere of the comet. And the Rosetta spacecraft had an instrument that was collecting dust particles. And you can see a scheme of this instrument that was called COSIMA. You had a series of collecting targets that were exposed outside the spacecraft for a few hours, a few days, and then from time to time the collecting targets were brought back inside the spacecraft and they were analyzed, first pictured under a microscope, and we got the images back to Earth and we could see, oh, we got dust particles on this target and we want to analyze this dust particle. So we moved the target in front of an ion gun and we were able to make tough SIMS, so time of flight secondary ion mass spectrometry, and then analyze the composition of those dust particles. So it was an extremely powerful tool, and you can see here on this slide a picture of a target. So you must imagine that it's only 1 centimeter per 1 centimeter, so it's tiny target which was exposed outside the spacecraft. So this picture was taken in May 11th, 2015, and this time we brought this target a few hours after exposition outside of the spacecraft, and this is the same target picture 24 hours later. And you can see that it's covered of dust particles. It's covered of matter ejected from the nucleus. You can see tiny parts of the cometary nucleus that have been captured in the instrument. So they were captured at a relatively low velocity, 10 meters per second or below. So it doesn't change the composition. It's splash, but it doesn't change the nature of the compounds that are present on the dust particle. And we've been able to analyze those dust particles. So we named those particles because when we were discussing with colleagues all over Europe about our analysis, we are naming. So Kenneth and Juliet were the first dust particle for which we really had nice and straightforward analysis of composition. And you can see here with this ion map the detection of carbon on the dust particle. So the lighter the color is, the more carbon is detected, and it's really at the surface of the dust particles. And here you see the mass spectra. So what are the ions that are ejected from the dust particle when you irradiate the dust particle, the surface of the dust particle with the ion gun? So actually, first we were a bit disappointed. We were expecting a large diversity of organic fragments. And it's not what we see. we see carbon, but carbon at the lower masses. We see quite easily carbon at mass 12, CH, CH2, CH3 at mass 13, 14, 15, and almost nothing else as an organic imprint. We see silicon, we see sodium, we see a little bit of magnesium, we see a little bit of iron, and on those plots, what is red are the measurements on the dust particles, and what is black are the measurements near the dust particle. It's an expression of the background of the instrument. So it's a clear cometary signal, but not an expression of a very large diversity of structure that we were expected, but something else. And it took us a lot of time to figure out that this kind of signature with our mass spectrometer, because it's a unique mass spectrometer, it's been built for this mission. You cannot buy another one in the commerce to make the same measurements. So when the COSIMA instrument was built for the Rosetta mission, another one was built, the ground instrument. And it's only with this ground instrument that we can compare the way the material interact with the ion gun and make comparison and make a library of spectra from this ground instrument. And after a few months, if not years, we figure out that this kind of signature is relative of a complex macromolecular organic structure. And the best match we had, at least when this paper was published in 2016, was insoluble organic matter extracted from Murchison meteorite and other chondritic meteorite. So it showed us that there is some kind of link between the organic material that is found in meteorite and the organic material that is found in comet. It's not, as you can see, exactly the same signature. The CH, so the abundance of H, is higher in the comet than in the chondrite, but it's related. It's the same kind of material. And in our library, we had a lot of compounds that had been analyzed. You can see aliphatic compounds, aromatic compounds, nucleobases, carboxylic acids, nucleobase, and each of those molecules would yield what you can see on the right, some specific fragments and a diversity of organic fragments at higher masses than those we actually detected with the COSIMA instrument. So it's not that kind of material. And the material that can be related to what is observed in the Comet 67P is the same kind of material we observed in meteorite, insoluble organic material. And here you see a complex pattern, but for me it's too simple. It's not really realistic because it can be drawn on a piece of paper. What we are facing is probably more something like this that you can see on the right part of the slide. A complex three-dimensional organic matter that is made of carbon, hydrogen with a small amount of oxygen and nitrogen and also probably a sulfur. And this 3D representation is not a representation of insoluble organic matter, but I found it in a paper describing kerogens. Kerogens are organic material that is found on Earth, and which is also a complex 3D matrix of organic matter, and it has the same kind of response with the COSIMA instruments than what we found in our library. So this is what is observed, but how much? We've been also able to estimate the amount of elements and the amount of material that is found on those dust particles. Remember, in the chondritic meteorite, the amount of carbon was at most 5%. In the dust particle of Comet 67P, we have roughly 30% in number of carbon, 30% of oxygen, and 30% of hydrogen. This is in number. In mass, it would be roughly 30% of carbon and 40% of oxygen. All of the oxygen is not necessarily in the organic phase. It is also linked to silicon and in the mineral phase. So our best estimation at this stage is that the dust particles are made roughly of 50% of mineral and 50% of organic material. So 10 times more of organic material in the dust particles of Comet than the organic material found in Comet, than the organic material found in meteorite. And if you make some calculation and estimation in volume, you can consider that the dust particles are made roughly of 70% of organic material. So there's a huge amount of organic material that is found in those dust particles. And if you want to have a better picture of the composition of the comet, if you look at the pie chart on the left, you can see how the carbon is dispatched in the comet. So some of the carbon is in CO and CO2, frozen on the nucleus. A tiny amount of carbon, up to 2%, is in the large diversity of organic compounds that are observed in the atmosphere, and almost 90% is present in the form of this complex organic material. And if you add the other gases that have been observed, the minerals that have been observed, you can see on the right part of the pie chart what is our best estimation of the global composition of the Comet 67P. So this complex organic material would represent 1/3 of the comet in mass, and the small and large diversity of organic compounds would be roughly 1%, up to 1%. How did we get all this complexity in comets and meteorites? It didn't appear at once. It's the result of a complex evolution, chemical evolution. I cannot dig into all the direction of research about this, the origin of this complex material, but I just want to mention one kind of experiments that are made in the laboratory, in various laboratories around the world. This can be seen as a Miller experiment, but at low temperature, simulating what happens in the interstellar medium or in the first phase of the protostellar nebula when the solar system formed. So you start with frozen compounds, simple compounds such as water, ammonia, methanol, for instance. You would freeze those compounds on a cold target, and then you would irradiate those compounds, for instance, with UVs. And a complex chemistry will occur when you irradiate those compounds. And if you let the temperature of the experiment, you start at 10 Kelvin, 10, 20 Kelvin, and then you let it rise slowly back to room temperature. So all the ice will be pumped out from the experimental device. But on the target would remain an organic residue. And this organic residue, you can see a picture of it here. Another picture of this organic residue can be seen here. Most of it is soluble. It depends on the amount of energy that has been deposited on the ice. If you irradiate a very long time, you will get less and less of soluble fraction and more of insoluble fraction. And when you analyze the soluble fraction, you will find a large diversity of organic compounds. Any kind of chemical family you can think of is represented in this organic residue. So just the simple fact of irradiating an ice made of water, ammonia, methanol, or other starting material would lead to this huge diversity of organic compounds. And Of course, in these experiments, since amino acids are so iconic in prebiotic chemistry, people are looking for amino acids, and amino acids can be found. But they are found only after some chemical preparation and acid hydrolysis, for instance, and after being in liquid phase for some time, and only glycine is observed before any liquid phase during those experiments. So you can see here a detection of many compounds, but after this specific preparation, an acid hydrolysis at more than 100 Celsius and at very high concentration of hydrogen chloride. So you have to keep in mind when you read about this very interesting experiment that it's not necessarily what you get straightforward in the ice, but it's what you get straightforward after the whole preparation before the final analysis. And during this preparation, some chemistry may occur, and so it has to be considered. I've talked a little bit about chirality previously during this lecture. With this scheme, it will be maybe easier for you to understand if you're not a chemist. So these are two configurations of the same amino acid, and there are an image from one to another in a mirror. And I told you that in some meteorites, some amino acids are found with some enantiomeric excess, a few percent, up to 10, 15%. And recently, some experiment conducted in the laboratory, the same kind of experiment I've just talked about, so some molecules that are frozen at a cold temperature, but that they are irradiated this time not by UV, by a classical UV lamp, but they are irradiated with polarized UV lamp. And according to the way the UV light is polarized, you would get excess of amino acid of one configuration, or if it's polarized in another direction, you will get excess of amino acid of another configuration. So one idea to explain the excess of amino acid is that this excess could be the heritage of an irradiation of ice by light that had this specific polarization. And in the interstellar medium, it's been observed that some stars at some stage of their existence can emit polarized UV, and this could result into this enantiomeric excess. And it's interesting to think, it's not demonstrated, but it's a scenario which is built on experiment and observation. It's interesting to think that maybe life chose the L configuration because meteorite brought to Earth a small excess of amino acid in the L configuration. And then, since this excess was present on the primitive Earth, it has been selected because more abundant, and then this excess has been amplified by life itself. So, enough of small bodies and a few minutes now on Mars. So Mars is one of the dreams of the astrobiology. It's close to us. We have this idea and proof that there was liquid water on Mars during a few hundreds of million years of its history. Well, we know that at least meteorites fell at the surface of Mars, and they may have brought organic matter at the surface of the planet, and, well, energy, light from the sun or other process. So there's, well, a lot to think and imagine about Mars. It's been proven that water in the liquid form was present at the surface of Mars by geological analysis, mostly thanks of the rovers that made precise analysis at the surface of Mars, but also by mapping with space missions that are orbiting the red planet. But, well, if you land on Mars, you see a red surface, you see rocks. And in 1976, the two Vikings missions were devoted to looking for life and looking for organic matter, and all the experiments that were extremely impressive for the 70s, they worked, at least technically they worked, but the results were not conclusive because the Mars environment, the soil of Mars is extremely oxidized. It's also extremely oxidant. It contains perchlorates. And when you run an analysis of the soil of Mars looking for organics, most of the time you get into a lot of troubles because of the nature of the soil. And since 2012, the Curiosity rover landed at the surface of Mars, and he made a lot of analysis of the soil, and well, we finally found organic matter at the surface of Mars. But tiny hints, things that are not yet settled. We don't know exactly what are the original form of organic matter in the soil of Mars. For instance, you probably heard about the detection of methane. The Curiosity rover detected methane at the surface of Mars. It's been discussed because, well, it could have a geological origin, but some people say that it might be produced by microbes. And methane shows cycles in abundance at the surface of Mars. There are spikes of methane that are observed. It is what you can see on the left panel. You can see the blue points spiking on a specific depth. And on the right panel, you can see at a very low level, below 1 part per billion in volume, you can see a seasonal change of methane that are observed. So those are observations that are made by the Curiosity rover at the surface of Mars. And those are the various explanations that are shown, and this hypothetical source from microbes. When you use the most recent instruments that have been sent to Mars to detect molecules such as methane, the ExoMars Trace Gas Orbiter that is orbiting Mars since a few years from now, with instruments that are really dedicated to the search of methane, well, one of the most recent papers from this spacecraft conclude to the no detection of methane on Mars from early ExoMars Trace Gas Orbiter observation. And it's still a debate in the community whether or not the detection of methane from the Curiosity rover is really a detection of methane, because if it's really detected, it should by Curiosity, it should be detected also by Trace Gas Orbiter. And there are still a lot of studies, people struggling to try to match the two observations, whether or not methane is detected or not at the surface of Mars. Here you see a chromatogram of the organic compounds that have been detected by the SAM instrument inside the Curiosity rover, and you can see that most of the molecules that have been detected contain chlorine. The green dots on the molecules are chlorine. It's certainly results from a combination between the organic matter that is present at the surface of Mars, that is collected in the soil by the instrument. But this organic matter is analyzed, processed during the analysis, and it will react because it will be heated during the analysis. It will react with the oxidant present in the soil of Mars and then generate new compounds. So what you detect is not necessarily what is there. It's a combination between what is there, what is within, what is with the organic matter, and the analytical process. And there has also been sulfur-bearing compounds detected at the surface of Mars, which are probably the result of the decomposition of macromolecules containing sulfur, but those macromolecules are not detected. It's the result of the decomposition of those macromolecules, and also more recently some aliphatic compounds that have been detected at the surface of Mars. So it's extremely difficult because when you go in the solar system, you build an ambitious space mission, you build instruments, and well, you go somewhere for the first time. And when you arrive for the first time somewhere, then you discover the whole environmental parameters. And these environmental parameters would interact with your analytical process and might interfere with your detection. So, well, probably to get a final word about Mars and what is inside the soil of Mars and whether or not there was life on Mars, we would need sample return. Because if you are on Earth, then you can analyze with some instrument and say, no, it's not the best. Because this kind of interaction we never thought about with the sample. So let's change the analysis, let's change the instrument, and it's more versatile, and you can do much more if you are on the Earth. As I said in the introduction, I will skip very quickly on the icy moon. They are very fascinating because, well, there might be liquid water beneath hundreds of kilometers of ice on Callisto and Ganymede, and maybe for Europa a few tenths of kilometers of ice. You can see the structure of this icy moon. For Titan, you have an atmosphere, so organic chemistry can occur in the atmosphere of Titan. You have a certain depth of ice, water ice. So for the largest icy moon, more than 100 or 200 of ice, then liquid water, and another layer of ice between the liquid phase and the rocks, and maybe potential hydrothermal vents that could be at the surface, at the rocky surface of the planet. For Europa, since the planet is smaller, the moon, not a planet, the moon is smaller, the ice layer would be thinner, and the liquid phase would be directly in contact with the rocky surface. So that's why one can imagine that there might be organic synthesis and some energy provided in hydrothermal vents that could be in the depth of the ocean of Europa, but it would be the same for Enceladus around Saturn. And well, we can think about potential life in the ocean of the icy moon. This is extremely hard to think about digging through tens of kilometers of ice to make analysis, but that's, well, maybe for the future generation of scientists exploring the solar system. Enceladus is smaller than Europa, but probably has the same structure: ice, liquid, and the rocky core of the planet. And what is interesting with Enceladus is that we can see plumes of material that are ejected, and those plumes are thought to come from the ocean. So you don't need to dig, maybe, for Enceladus. Maybe you just need to fly by Enceladus with the best instrument you can imagine, or just land at the surface of Enceladus and collect samples that could be delivered from the depth of the liquid ocean inside the moon to try to figure out what is inside the moon. Titan is also an interesting satellite because it has an atmosphere, and in the atmosphere itself you might have a lot of organic synthesis, and they may be the first steps of the chemical evolution that may lead to a complex chemistry, and maybe chemistry leading to life. But you have to keep in mind that the surface of Titan is frozen, and if there is liquid ocean, they would be embedded below hundreds of kilometers of ice. I come to my conclusion. I started with these ingredients of life, and I hope that even if it's an axiom, it's worth to study this path, looking for a combination of liquid water, organic compounds, and energy. Maybe it's too optimistic to jump to the conclusion that necessarily there would be life in the ocean of Europa, as you can see on this scheme. And this scheme is extracted from a NASA website describing a space mission to Europa. We have to be extremely conscious. And one of the leading chemist in the field of the origin of life, John Sutherland, actually recently wrote that, as I said earlier, a requirement for ultraviolet radiation to generate hydrated electrons would rule out deep sea environment for the origin of life. This, along with strong bioenergetic and structural arguments, suggests that the idea that life originated at vents should, like the vents themselves, remain in the deep bosom of the ocean buried. We have to keep that in mind. I'm not saying that is right. As long as we don't find life somewhere else, we can imagine and make hypotheses, various hypotheses. But we cannot go to those icy moons saying, well, for sure there will be life because there's liquid water, organic matter, energy, ignoring those chemists stating that there is those specific requirements from UV light. As a conclusion, I will quote again Sutherland, that says in the same paper in 2017 that, well, for understanding the prebiotic chemistry, we are not yet close to achieving this end, but recent results suggest that we may have nearly finished the first phase, the beginning. So we are in a time that it has become possible to really assess the potential of life in the solar system beyond Earth. It's going to be very long, and we shall proceed step by step. There is a real challenge for analytical chemistry and space instrumentation to deal with organic matter in previously unknown environments. And probably for the case of Mars, and maybe for the case of icy moon, but much later, there is a need for a sample return. We will really be able to understand our theories about life when we will be able to find another form of life, if we ever succeed in doing that. And even if we hear and we can dream about space exploration, we can dream about those world unknown around the giant planets or beyond our solar system. But we have to keep our feet on the ground as scientists, even on Mars or in the fascinating ocean of Europa and Enceladus. But it doesn't mean that we don't need to explore them. Thank you for your attention.